Well, we're going to use law of cosines. Well, I'm going to use the law of cosines if I have side angle side or side, side, side. All right, and that pretty much covers all of our possibilities for triangles. So that section on the test, you should have this memorized, so you're not spending the whole time trying law of cosines and figuring out you don't have enough information to fill something in, and then going to the law of sines and then trying that out. So when I give you the triangle, just figure out which one you have, and I'll tell you which one to go to. Remember, law of cosines, I actually gave you two possibilities, but it all boils down to that a squared equals b squared plus c squared minus 2bc times the sine of a. This was just a manipulated form. It could save you some time on the test. Okay, any questions on that? Or why we're going over that? Or why that's important? We're good on that? Okay, do we have questions on the homework minus the fact that number 2 was actually number 3? If you looked in the answer guide, it was actually number 3. We were good on that, though? Okay. I was hoping. Was it easier? Was it better than the 2 before that? Yeah? Okay, good. All right, today I'm going to talk at you a lot. I guess it's the best way to describe it. It's a longer assignment, longer lecture, so it's actually a shorter assignment. Okay, if you look at the assignment, it's actually just 1 page and a quarter, and it shouldn't take you that long. The hard part about vectors is it's going to be a bunch of information thrown out at you. All right, so it's going to take practice, and it's going to take looking over and memorizing stuff. Possibly, maybe I'll give you. I'm thinking maybe in this chapter, because it's such an oddball chapter, I'm thinking possibly I'll give you what I call a mad card. It's you might be able to have, and remind me of this because I'll probably forget it. You can have like a note card, and you can put whatever information you want on it. All right, minus specific examples. Just because this is just a mixed bag of a chapter. Usually I'd split it up, but I don't have time right now. So we're going to go through it and possibly use that to help it. Okay, so we're going to talk about vectors today, and we'll talk about vectors on Monday as well. A vector is just a directed line segment with both magnitude and direction. Magnitude is just length. So all we're saying is we have a line that has a particular direction and it has a particular length. And vectors most look like a ray, except for they have a starting point and an end point. And you probably saw rays a lot when you were in physics, for those that didn't block out that whole semester or year of that. All right, so let's go ahead and draw a vector. So a vector would just look something like this. It would just be a line with an arrow at the end. The only difference is it has an exact start point and it has an exact end point. Now, a lot of times we don't actually put this point up here. It's just assumed it's there. And I'm going to label this A, and I'm going to call this B. That's a vector. It's got a particular direction, and it has a particular length. That's our magnitude. It's how far apart A is from B. So let's just do some notation really quick. So notation. So with notation, there's 2 ways to signify a vector. The first way is we write down our start point, which is A, and our end point, which is B, and we put a little arrow on top of it. It almost looks just like a ray notation. But when we're talking about vectors, it becomes vector notation. Now, this is most commonly used when I'm writing by hand. Because as soon as we got typewriters and stuff, we came up with this bold-faced stuff. So another way we could note this, or you can actually use a bold-faced letter. It can be uppercase, it could be lowercase. And a lot of times we use V. So this is actually a bolded V, and I think I'm going to actually, let's just change that size. Let's make it a really good bolded V. And that's a bolded V, which in math we call boldface. All right, so the book's going to use a lot of boldface because it's easier to type that than having to write A, B, and put an arrow above it. It's just a V. And you'll probably find a lot of times you'll just write that V and just know that it is a vector. So we could either do an AB with an arrow above or a boldface V, and we can use any letter for it. It could be a boldface B. It could be a C. It could be whatever we want to name that vector, so it's any letter. It's not always V. The other thing I want to talk about is magnitude really quick. So when I talk about magnitude, all we're talking about is length. How long is that line? And if you remember from physics, vectors are usually used to talk about force. So that length might be 40 miles per hour. All right, that length might be 40, but it stands for 40 miles per hour. It might be how much force of pounds you're putting on something. So that could be 20 pounds of force. That length of 20 would actually stand for 20 force pounds. So length of that line is our magnitude. The symbols we're going to use for magnitude, we can use an absolute value bar around the name of the vector. So it might be absolute value of vector v, or we can put the absolute value bars around AB. So both of those are going to stand for our magnitude. Note the absolute value signs. The absolute value signs are there for a reason. Our magnitude is always going to be positive. If my wind is going east at 40 miles per hour, it's still going to be 40 miles per hour. I'm not going to say the wind is going negative 40 miles per hour. I don't think they ever say that on the weather. The wind today is going to be a negative 20, gust up to a negative 40. I don't think they've ever said that. So our magnitude is going to be positive. It's a positive length. You're measuring something. And whenever I measure something, it's always positive. Okay, so those are the basics of what a vector is and what the magnitude is. And I don't think I missed anything. Let me just double check my notes. Kind of left kind of a blank spot for me. All right, yep, we got length, we got positive. Okay, the next thing we're going to talk about is scalar multiplication. So like I said, vectors are a lot of times used for force. So what this diagram is showing is we have two tugboats. We have a bottom tugboat and a top tugboat. Well, the bottom tugboat is exerting this much force. We call it vector A. This one's applying this much force, which is 2A. So the longer the line, the more you're actually doing or the more force you're applying. So, based upon this picture, if the bottom tugboat exerts 2,000 pounds, then that top one must be exerting 4,000 pounds because it's twice as long, and it's denoted by that 2A. And this is known as a scalar multiplication. I'm not changing the direction of my force. All I'm doing is multiplying it. I'm either making it more force or I'm using less force. And we're going to draw some pictures to signify this scalar multiplication. So if I start with just a vector, I'm going to call this vector A, B. So this is vector AB. Yeah, go ahead. So a scalar multiplication of vector AB might look like something like 2 times AB. That means I'm putting twice as much force, or my vector is going to be twice as long. It's not going to change direction. It's still going to go in the exact same it's just twice as long. So that is my AB. That is twice my AB. That's about twice. That looks pretty good. We're not always making it bigger. A scalar effect can actually make it smaller. And what's going to make it smaller is if I multiply it by, say, 1/2. So if I do 1/2 a scalar multiplication of AB. So that's going to be the exact same direction. The only difference is it's going to be smaller, about half the size. So that's my half AB. The only way a scalar multiplication can actually change the direction of a vector is if it's negative. If it's a negative scalar, it's going to reverse the direction. So if I'm going in this kind of arrow, and I'm just going to reverse the direction, but the line's going to stay the same. So an example of that might be if I have negative scalar multiplication of AB, Our line is going to look just like that original vector. The only difference is our arrow is now going to point down instead of up. Our B still stays up here and our A is down here. So in effect, by multiplying by negative, we change our start point and we change our end point. So the little note I put by this one is, if I have a negative scalar of AB, that's actually the exact same thing as BA. A positive BA, because my start point was B, my end point was A. So those two things are identical. So a negative flips the direction, puts in a reverse. It's just like if I decide to throw this tugboat in reverse, this arrow is still going to go this direction, except I'm going to point that way. I'm now trying to push the barge that way instead of trying to pull it. Okay? And that's our scalar multiplications. We're going to talk more about that, I think, on Monday. Would be a good day to delve more into scalar multiplications. All right. Sometimes we're going to add or subtract vectors. And an example of that might be, let's say I have a barge here. We'll stick with the barge and the boat. Maybe I have one tugboat pulling, so it's connected at one pulley. And I got one tugboat pulling that direction, one tugboat pulling that direction, so they're not hitting each other. I want to know how much force is being applied to this barge when I add those two things together. Because it won't be just adding their two forces to each other. Because this one's going in a different direction than this one, so we lose a little bit of force. So adding, when we add vectors to each other, it is actually pretty simple. All it is, oh, I should label it first. Let's go ahead and label these. I'm going to label this guy A. I'm going to label this guy B. All right, so we have A and B. Yeah, we're fine labeling them there. All right, the first addition I'm going to do is I'm going to go A plus B. So I'm going to go from A plus B. In order to do that, I'm going to go all the way out to the end of A, and I'm just going to add B onto it. All right, so I'm going to take B's length and direction and put it right on the end of A. So that's going to look something like this. All right, then I'm just going to put a point there. Let's go ahead and put it in blue. We put a point there. What did I pick? Blue. And we just connect that point. And this line right here is going to be A plus B. Symbology-wise and conceptual-wise, this is different than B plus A, except it's going to result in the exact same answer. If I had to do B plus A, instead of starting with A, I'm going to start with B, and I'm going to add A onto it. So if I had to do B plus A, I would go that direction to that exact same point. Except on this side, I'm going to say this one's my B plus A, because I started with B and I attached A onto it. Not overly critical that we do that perfect with addition, because we see they both come up with the exact same answer. It's going to be different, though, if I did subtraction. We have to be careful of what we do with subtraction. So with subtraction, I'm going to call this guy A and this guy B again. I'm going to do B minus A. So B minus A tells me to travel up B and subtract A from it. Remember, if I have a negative vector, it goes in the opposite direction. So if A goes this direction, negative A is going to go in that direction. So B minus A for a vector is going to look like this. Because that up there is actually negative A. So this line I just created that line right there is going to be B minus A. We really don't have room for it, but can you kind of picture what would happen if I had A minus B? So if I have A here, and I subtract b, so it'd go in the opposite direction, that a minus b would end up somewhere down here and it'd actually make a straight line. This would actually make a straight line. However, if I did the subtraction wrong, I'd have the wrong answer. So if I asked you to do b minus a and you started out here and subtracted b, it'd be completely the wrong answer. All right, this method is called tip to tail. Because you attach the tip of one with the tail of the other, and you just run up that one. Tip to tail. I'm never going to ask you, did I use tip to tail, but it's good to know. All right, so that's adding and subtracting vectors. I think that's like the first thing you have to do in your homework, and it's just like drawing. Maybe it's not the first thing. Okay, the next thing I want to talk about is horizontal and vertical components. Like I said, every vector has direction. And just like anything on the xy plane, it has a horizontal movement and it has vertical movement. Now, with vectors, it's always a good idea to know how far it's moving horizontally and how far it's moving vertically, because those forces can be integral in solving different problems, especially in physics. So we're going to look at our horizontal movement and our vertical movement. We denote those with W sub x and W sub y. Just think about that. W sub x, x-axis, horizontal, y, vertical. All right? So, first of all, we have a directional angle. We have a directional angle telling me where this vector is going. So we have a directional angle. And what I'm going to look at here is this point where it ends actually creates a right triangle. So that means this angle has something crucial to do with this W sub x. If I have a right angle, and I happen to notice that this is adjacent, and then I'm going to look at this length here. So I'm going to let R stand for my magnitude. So that R is my magnitude. I'm going to maybe put that up here. R equals my magnitude, which is my length. So in this example, I know the length of this line, and maybe I know the length of this line, or how do these two things relate? Well, I have a right triangle, and I have an angle. So anytime we have a right triangle and an angle, we should automatically think of SOHCAHTOA. We should always think of our trig functions. So if I'm looking at this angle, this is adjacent, this is hypotenuse. That sounds a lot like cosine. SOHCAHTOA, adjacent over hypotenuse. So we're just going to set up an equation. We're going to say, depending on what I know, well, cosine of that theta, or that angle that we're talking about, well, that's going to equal my adjacent, which is my horizontal component, or W sub x, all over my hypotenuse, which happens to be my magnitude. My magnitude is my length of my hypotenuse. Well, working our way down, I multiply both sides by r, so we're going to end up with our horizontal component just equals r times the cosine of theta. Now, if you want to, you have room down here. I don't know why I put this down here. Because you can have it right here and circle it, and you'll be good. So whenever I'm talking about my horizontal component, you can think of that as my x value, or we're going to talk about later as my a value. That's just going to equal r times cosine of theta. Now I want to do the same thing for my vertical component. My vertical component, you can see, is on the opposite side here. It has nothing to do with this angle right now. However, this length, that's the exact length as this one. So I'm just going to, I know, right? I'm just going to rewrite that over here. I'm just going to say, hey, if that's wy over there, this is also wy, so I can use this exact same angle. So now I no longer have adjacent over hypotenuse. Now I have opposite over hypotenuse, which is going to be our sine function. So our vertical component has something to do with sine, and that's going to be the sine of theta is going to equal my horizontal, or my vertical component over my length of my hypotenuse, which is also my magnitude. Multiply both sides by r, and you're going to see that your vertical component is just going to equal r times the sine of theta. That gets our vertical and our horizontal components. Just for the sake of later on, I'm going to change some notations here just real quick because there's other ways that we denote this stuff. All right, do you see this point that's formed right here? There's a point that's at the end of this. Just like we have x, y values, typically with vectors, we call this point a, b. We call that point a, b. So that means our wx value sometimes is called a, and our vertical component is oftentimes called b. All right, and we're going to see that later on. That's when we put it in component form, we use a and b. But for this next problem, we're going to talk about vertical and horizontal. All right, our example of this is find the magnitude and the horizontal and vertical components for a vector v with magnitude 8.3 and the direction angle 121.3 degrees. So we're trying to find the magnitude of the horizontal and vertical components. What I want to circle here is the fact that it says magnitude, right? Because that's going to signify that it must be positive. Magnitude tells me that it needs to be positive. So whatever answer I get out, if I forget to take the absolute value of it, at the end I should go, wait, I was looking for magnitude, it should be positive, just make it positive. Okay? So I'm looking for something that's positive. The first thing I'm going to do is I'm going to go ahead and draw. I'm going to draw this angle that they're talking about, or this vector they're talking about. So I'm just going to do an xy plane. And I'm just going to maybe approximate 121 degrees. Well, it's definitely bigger than 90, less than 180, so it must be somewhere over in this quadrant. And that means my vector is somewhere over here. That is my vector. And that is 121 degrees. 0.3 degrees. And it also says it has a magnitude of 8.3. So the length of this line is 8.3. So that's the vector they're talking about. I want to know what is the distance it travels this way and what is our vertical distance. All right, so I'm trying to find this distance and this distance. So I'm trying to, maybe I'll put that in purple. Nope, purple won't really show up. So this is my wx, that's my horizontal. My wy is going to be on this side, or my vertical. It's not overly important, but it's good to know what we're talking about and you're not just plugging things in for some reason. Although we can just plug stuff in now. Because if I'm looking for my horizontal, that is my w sub x, that is my x value. I'm looking for my x value. However, I'm looking for the magnitude, so I'm going to say wx, w sub x, I'm going to take the absolute value of whatever I get, is going to equal r times the cosine of theta, where r was our magnitude. R is our magnitude. So our magnitude here was 8.3, so we're going to have 8.3 times the cosine of our theta, which was 121.3 degrees. So I'm going to take the absolute value of all of that. I'm going to make sure that whatever I get is positive. When we plug that in our calculator, we're going to come up with absolute value of wx is going to equal the absolute value of negative 4.3. So that means our magnitude, or our horizontal magnitude, is going to be 4.3. So in fact, we travel 4.3 units in this direction. All right, so if I put a point at 4.3 right here and went straight up, I would hit the tip of this. So in fact, that's kind of like our x value. This is kind of like our x value, but positive. All right, let's go ahead and find our vertical. Our vertical is going to be the exact same thing. We're just kind of finding our y value, but we're making it positive. So we're looking for the magnitude, which means it has to be absolute value sign of our vertical. Well, it's almost exactly the same. The only difference is we're going to use sine instead of cosine. So we have the sine of 121.3 degrees. Once again, I'm just going to kind of plug through so we can get through this. Well, my absolute value of my vertical is going to equal 7.1. So that means if I go up 7.1 units, I would run right into the tip of this. So if I found the point, well, we'd have to actually use a negative 4.3 and 7.1. That would actually be this point right here. Yeah?
For the answer, do you want us to keep the absolute value?
So at the end here, why I kept this absolute value is because, and that's a really good question, because technically when we denote magnitude, we always use an absolute value to let the person know that, hey, this is the magnitude, that's what I'm looking for. Because if I just left it as w sub x, they're like, was it the magnitude or was that the point you're talking about? Because we'll talk about the points in a second. So that was a wonderful question. Yeah, use the absolute value bars whenever you're talking about magnitude. Okay, we're going to talk about component form, and then we just have two problems to get through. All right? And then I'll stop talking. So the component form of a vector is a way to denote the vector based on its horizontal and vertical components. This is achieved the same way we denote the horizontal and vertical components of a point on a graph. We just use the x value and the y value. The only thing different is because we are talking about vectors, instead of x values, we usually say, this is my a value. On the x-axis, we use an a value. On the y-axis, we're going to use a b value, which means that point where that vector ends is actually giving me the point a, b. So that's the point. To put a vector in component form, we're going to take that point, but instead of parentheses, we're going to use arrow brackets. So that's going to be a, b. That is component form. So you just find your terminal point, and you just put arrow brackets around it, and that is your component form. Now, what this means is we actually have two components. We have a vertical component, and we also have a vertical component as well. So I'm going to label those using component form. So that vector that ends in a, or that runs across our x-axis, is actually the component form that would be a, comma 0. That's that vector. The one that runs up vertically, that vector would actually be 0, b. It has 0 horizontal movement and just goes up to b. That's just a way to name those as well. So I'm just naming those. All right, magnitude. We're going to also talk about magnitude on this one. Notice that the vector creates a right triangle where the magnitude is the hypotenuse. And what I mean by that is if I would drop a dashed line down here, I would create a right triangle where our magnitude, let's go ahead and list magnitude here. Our magnitude is our hypotenuse. Well, one of our sides is actually going to be length b. So if we look at this one, the dashed line I just made has length b, where this line is length a. So if I needed to solve for this and I knew a and b, I would say, hey, guess what? My magnitude is just the hypotenuse of a right triangle. So if I had magnitude squared, that would equal side squared plus the other side squared. So a squared plus b squared equals c squared. Well, I'd probably take the square root of both sides. So I would just say, whenever I know my a value and my b value, or my component form, my magnitude is always going to be the square root of a squared plus b squared. So if I know these two values, I square them, add them together, take the square root, and I now have a magnitude. And if I'm taking a square root, it's going to be positive. That answer is going to be positive, so we're going to be okay. So I typically don't put an absolute value sign on that. All right, let's apply everything to these next two problems. All right, the first problem says find the magnitude and direction angle of the vector -2, component form -2, -5. So what you're going to do on something like this is you're going to plot -2, -5. You're going to draw your vector, and it kind of helps guide you of what they're looking for. So what I'm looking for is, the first thing I'm going to look for is my directional angle. I'm looking for how big is this theta. How big is this theta? So we're going to do our directional angle first. So maybe I'll just note directional first. Okay, so we're doing our direction first. Well, I can't start out by getting this full angle. I have no formula or anything that gets this whole angle. So my backup is always, if I'm ever on the unit circle, my backup is always make a right triangle and see if you can help solve it. So if I'm looking for the direction, instead of getting this whole thing, I'm going to draw a right triangle. Maybe I'll make it out of red. So I'm going to go ahead and make a right triangle. And that means I'm going to actually, let's call this beta in here. I'm actually going to figure out what this sliver is. Because how big is this? How far am I going from here to here? What do you got? 180. So I already know 180 of it. It's going to be bigger than 180. We're going to be bigger than 180 because we already have 180 on top. If I find this little sliver, then I know all of this information. Well, I have a right triangle, so if I know two sides, I can use sine, cosine, or tangent. Let's figure out which two sides we know. Well, if this is the point -2, 5, that means the distance from here to here is 2. So that distance from there to there is 2. And if this is -5, this distance is going to be 5. And you can either use -2, -5, or you can use a +2, +5. And I'll talk about why we can do that in a second. So this is -2, -5. Doesn't matter which one you use. It'll all come out in the wash in a second. So we're going to note that, hey, I have opposite and adjacent, so I'm going to use tangent. I'm going to say, well, the tangent of that angle is going to equal opposite over adjacent. To plug that on my calculator, I need to do tan inverse of both sides. So we're going to say that angle actually equals the tan inverse of 5 divided by 2. Now that's going to come out to, do I have the wrong page? That's going to come out to 68.2 degrees. 68.2 degrees. If that wasn't positive, so if I plug -2 and a +5 in here, that might not have been positive. What you're going to do is you're going to always have this as positive. Always make positive. And why we do that is because this has to be a positive angle. Because if this was negative, I'd do 180 minus something, which would be up here. So this angle always has to be positive. All right? So it already is positive. I don't have to do anything. Now I just have to add 180 to it, and I'll have the full circle here. So our final direction is going to be 180 plus that 68.2 degrees we just found. So that's going to be 100 or 248.2 degrees. That is our direction. That is definitely the harder of the two things to find, because to find my magnitude, we just learned that formula for it. So to find my magnitude, all we're going to say is, well, the magnitude of V is going to equal the square root of my A value squared, which is -2 squared, plus that b value squared, which is negative 5 squared. That means my magnitude is going to equal the square root of 4 plus 25, which is 29. And that's all the work you have to do, unless you can actually take the square root or simplify it. All right, so the direction is the hardest. Hardest of the two, you have to make a triangle. You're probably going to use tangent, and you're going to go from there. Any questions of what I did, or why I did, or did you think of a better way, or you just zoned out? It's Friday, and Mr. Pagan's talking too much today. It happens. All right, we just have one more example to get through. So try to stay awake for one more. All right, we're trying to find the component form for a vector of magnitude 40 miles per hour with the direction of 330. Once again, I'm going to make a sketch of it, except I don't know where it ends. I just know this length is 40. I don't know what my A is and what my B is, because that would already be my vector form. So we want to find our values of A and B. Well, if we take a second and we just go back to some notes we had, well, A is actually just our horizontal, our horizontal movement, and B is just our vertical movement. So we already have the formulas down for that. So what I put here is I just put recall that my vertical component actually equals r times cosine of theta, and my vertical component, wy, equals r times sine of theta. Well, A is just my horizontal movement. It's how far right I moved. And B is my vertical component, so we can just go right ahead and say that, well, A is going to equal my r times cosine of theta, and my B is going to equal r times my sine of theta. And we're okay with stuff being negative, so we're not going to put absolute value signs on anything. All right, so A is going to equal my magnitude, which is 40, times the cosine of my theta, which is 330 degrees. And my B, well, that guy is going to equal 40 times the sine of 330. And my two answers are going to be A. A was about 34.6. And B was about, oh, is it actually exactly negative 20, which means it's just like our XY values, except we're going to use arrow brackets. We'll have 34.6 and negative 20, because recall those arrow brackets tell me it's in component form.